action.
Yes, my name is Andreas, and I will talk to you about my project work on numerical simulation of circulation in boundary layers over sinusoidally modulated walls. So I will start with some background for this study. Some of you might or might have not seen streaks like this out on the ocean when it's a windy day. They are called Langmuir circulations, and they are formed by a mechanism that is driven by a higher order coupling between the shear in the upper layers of the water and the waves generated by the wind. The result is what you see on the top picture, and you can see what the Langmuir circulations look like in the shear layer on the bottom picture, where you have the wind direction blowing into the screen, and you have pairs of circulation cells forming in the upper layer of the water. This is an interesting phenomenon, both just it looks kind of cool, but also because it's contributing to mixing of mass, momentum, and heat between the water and the atmosphere, and it's also therefore contributing to, or it's important when you try to model climate and temperature. How is this connected to what I'm doing? Recent research by my supervisor, Simon, and his colleague have found, using theory, that the Langmuir circulation phenomenon is applicable on the when flow is flowing over a wavy pattern, as seen on this figure, because the interaction between the shear and the waves is still present in this problem, even though the wavy pattern has been shifted from the flow itself to the boundary. The implication of this could be that by forming these circulation zones, transport of turbulent kinetic energy can cause the viscous drag to be reduced. And it's interesting, and it could be important to characterize and study this phenomenon. The focus on my project work has been to identify, first of all, this circulation, and if that was possible, to also characterize a parameter space to see how different parameters will affect the flow. So, here's the fluid domain. Like it can be said, I've done this using CFD. So here's the fluid domain with some simple annotations describing it. The grid lines are not mesh. I realized that could look like it, but it's just so that you can see the wavy pattern in the geometry. It's modeled as a periodic domain, both in the streamwise and in the transverse directions, and then you have no-slip wall conditions on the top and bottom to form the shear. The flow is driven by a momentum source term that is varied. What have I done? I've done a literature study on the little theory that exists on this, because this is quite new research. I modeled the problem using ANSYS Fluent, so using parameters and just getting the simulations to work first. I've done a mesh study using different mesh parameters, refinement, and inflation layers in order to ensure that I get a solution that is converging with the grid. I've done this with laminar flow of different degrees, so I have been able to do it in steady state, so it's quite simple to do a grid convergence study, because you can just probe values in the steady state and see how they converge to some solution when you refine the grid. I've done a parameter study where I've altered the two parameters that I have considered the most important, which is the Reynolds number and also the angle of the undulating pattern, which I've tried to illustrate here in this figure, which is when you have a large angle, or you can say when you change the angle, you basically stretch the domain. So by stretching the domain and doing like a systematical preservation of different non-dimensionalized parameters, you can define a parameter space, which I will not go too deep into here. And then it's been doing a lot of simulations with these different parameters. And then we go to some results. Here you can see some figures. I can just first describe what the geometry patterns here are. To the left you can see a cross-section that is normal to the flow direction. So you basically just look into the flow domain here. And all the quantities are averaged in the streamwise direction to get a picture of how the net circulation or flow is throughout this periodic domain. So here on the left we plotted some streamlines which show very clearly the circulation pattern that I was supposed to identify, which match very good with the base case study that I have adopted from the work of my supervisor and his colleague. They have done the simulations using the lattice Boltzmann method, which is like a different method for CFD, which is instead of solving continuum equations like the Navier-Stokes equations, you instead solve kinematic equations on a much smaller scale. But qualitatively and quantitatively, these results show very good correlation, so that's very good. On the right, I've tried to quantify or show the quantification of the results with a non-dimensionalized vorticity in the streamwise direction of the vector field. That is the averaged vector field in the normal plane, which show, and I also added the tangential vector field over it, so you can see like the corresponding zones where you have pairs of counter-rotating cells that is fully equivalent to what is seen here in the bottom figure. Yeah, so here's the base case. That's a friction Reynolds number of 25. In the laminar case, you can think of the Reynolds number, the friction Reynolds number is approximately, if you square it and take 2/3 of it, then you have the normal Reynolds number for a plate channel flow. It's a little smaller here because you have some pressure-induced drag in the by having the undulations on the wall, basically roughness. And the base case also have the theta value of pi over 8, which means that you have an elongated in the y direction or in the transverse direction compared to the streamwise. Some other results, lowering the Reynolds number results in the circulations not fully developed yet. So you see, first of all, on the right, you see smaller values for the circulation, but you can also see on the left, the streamlines haven't actually formed full circulation cells. By increasing the angle, you can actually see that, or it's not maybe so apparent, but if you switch between these, you can see that the circulation actually has switched direction. If you compare like the colors on the right plot, which also is well corresponding to the theory and the results of Simen and his colleague. And finally, some results by increasing the Reynolds number too much. Then you can see that the vortex formation or the vorticity cells actually becomes unstable. It's important to note here that this is a steady-state laminar solution. So this is not a still image from the flow. However, by doing the steady-state simulation, when the flow starts to diverge, because the flow is so accelerated that it becomes turbulent, then yeah, you won't reach a steady state solution. So if you just stop it there and plot the results, then that's how it is. Yeah, looking in the in that case. So preliminary conclusions: circulation cells are identified using the CFD model that I have used. And also the results correspond well to the range of parameters that I also chosen on the base of existing papers. Further work will be how to study how the circulations affect the viscous drag. So looking at how the friction, just the tau wall affects is affected by these circulations. And in addition, it can be really interesting to do a DNS study of this for my master's, looking at how and when you reach the exact transition and how the vortices go from a stable steady state to a non-steady, unsteady pattern. So yeah, that's, I think, all that I had.